With that, what I'd like to do is introduce today's speakers. There are two faculty members who are joined with today, very honored and our esteemed guests. The first is Professor Stephen Boyd. Professor Boyd is a Samsung Professor in Engineering and the Professor of Electrical Engineering at Stanford University. His current research focuses on convex optimization applications in control, signal processing, and circuit design. Professor Boyd received his A.B. degree in mathematics, summa cum laude, from Harvard University in 1980, and has a Ph.D. in electrical engineering computer science from UC Berkeley, and he received that in 1985. In 1985, he joined the faculty of Stanford's Electrical Engineering Department. Professor Boyd is the author of many research articles and 3 books: Linear Controller Design, Limits of Performance, Linear Matrix Inequalities in System and Control Theory, and Convex Optimization. Professor Boyd has received many awards and honors for his research in control systems engineering and optimization, including the Office of Naval Research Young Investigator Award, the Presidential Young Investigator Award, the IBM Faculty Development Award, the AACC Donald P. Ekman Award, and is a fellow of the IEEE. We're also joined today by Professor Simon Wong. Professor Wong is the Vice Chair of Electrical Engineering and a professor there. He received his bachelor's degree in Electrical Engineering and Mechanical Engineering from the University of Minnesota and his MS and PhD degrees in engineering from the University of California at Berkeley. We're glad that both these faculty who have UC roots have joined Stanford University. His industrial experience includes semiconductor memory design at National Semiconductor and semiconductor technology development at Hewlett-Packard Labs. He was assistant professor at Cornell University from 85 to 88, and since 88 he's been on the faculty of Stanford University, where he is now professor and vice chair of electrical engineering. His current research concentrates on understanding and overcoming the factors that limit performance in devices, interconnects, on-chip components, and packages. He is also a fellow of the IEEE and has served on advisory boards of Altheros Communications and Pericom Semiconductor. Now I'd like to turn the floor over to Professor Wong, who will walk us through EE Future as we see it here today.
Good morning, everybody. Can you hear me? Okay. Welcome to this presentations where we would like to tell you where we see the future opportunities of electrical engineering would be. So if you go back at history and look at what we have accomplished, these are many companies that have been started by Stanford faculties or alum, and you can see that we indeed have been very successful in generating new applications based on electrical engineering. So what have we done? Our strengths are in fundamentals. We understand physics very well. We understand how we deal with very complex math. And combining the two, we are very skillful in developing models that describe the physics to the point that it will allow us to perform very detailed analysis of very complex systems and also innovate design for very useful systems. So in essence, we solve real problems and we find new applications for our technologies and math. Okay, if you look at some of the major innovation that has occurred over the last few decades, it sort of always occurs at the intersection of science and math. For example, if you look at integrated circuits, we start off understanding electrons and semiconductors, but that's not enough. If that's all we did, we end up with just a whole bunch of individual transistors. But being able to develop the math that describe very complex systems, in particular linear systems, being able to solve these matrix of equations using sparse matrix techniques, simulation and annealing allow us to design very complex integrated circuits. Of course, expanding that to the discrete domain allow us to design microprocessors that power the whole computing industry. You can also look across, for example, in communications areas. It's been around for many, many years. But the recent boom is basically taking our knowledge on electromagnetic wave propagations and combining that with the ability to process digital signal very effectively and understanding statistically how these signals will behave. so that we come up with digital wireless technologies. Similarly, in the optical communications, it is the integrations of understanding how photons behave, understanding how we can manipulate the photons, understand the statistics of how they will behave in the large-scale systems, and how do we extract the useful information out of that. So, so usually these creation of new application area, new company, or new industry usually occurs right at the intersections. So as we look into the future, what are the new intersections? What are these new big circles that might occur? I think that's what we are trying to address today. Okay. One thing that power all these innovations, of course, Moore's laws, which allow us to pack many more transistors onto a chip. It's been very amazing how Moore's law has continued to be able to progress despite of all the technology challenge. We're crossed over 100 nanometers over decades ago. We're now about to cross over 10 nanometers, approaching 10 nanometers. There's been a lot of prediction that this is all about the limit. I don't believe that is the case. I can remember that when I was a grad student, crossing under 1 micron was very, very difficult. And we did indeed cross over that. And then when I became a faculty at Stanford, going under 100 nanometer was almost impossible. And we did that. And so I think this path of progress will continue. Of course, it will require more innovation in science and technologies. And there's no doubt that the cost of doing this will become increasingly higher. However, I think there's other approach that we're also looking at that will also enhance scaling. If you look at scaling is really not just about putting more transistors on a chip. It is giving the consumers functions at a lower cost. So if you have other ways that can achieve that, that could also be possible. So one thing that might happen, or is already happening, is three-dimensional integrated circuits, as illustrated in the next slide over here. If you go and buy a chip today, a lot of them, for example, your flash cards already have multiple chips stacked, one on top of each other. So this allows us to increase the device density without any significant improvement in technology. All it needs is more sophisticated packaging or bonding technologies. Wafer stacking multiple wafers is already close to productions. In fact, some foundry has already announced that they will be providing this type of service towards the end of this year. Of course, the ultimate goal here is to allow us to monolithically stack transistors right on top of metals. This is an area where we're conducting advanced research in. So the next slide illustrates to you what one can do if indeed one can fabricate transistors at less than 400 degrees C. This slide illustrates a germanium MOSFET that's been fabricated at temperature less than 400 degrees C. And of course, with such a low temperature, it means that we can fabricate a transistor right on top of metals, which allow us to stack transistors right on top of each other, right on top of all the metallization layers, align them perfectly, and fully interconnect all these multiple layers of transistors. And you can see that one advantage of germanium is that the PMOS, the holes, actually have better mobility than silicon. So not only that we're allowing three-dimensional integrated circuit to happen, we're actually providing high performance device. So I think it's these types of innovations that will allow us to continue to progress according to Moore's law, but in a different way that we have done in the past. There's another whole area that we haven't even explored, which is to put photons on top of chips. Here's again because of the advancements of patterning technology. We're now looking at quantum photonics. You can see that we build quantum dots. All these quantum dots allow us to manipulate light more effectively. We can do quantum information processing, allow us to send signal from one part of the chip to the other part of the chip with optical means. And so all these things will also allow us to integrate not just electron on chip, but also photons. And again, that will allow us to progress in accordance with Moore's law, but again, in a different dimensions. Okay, so what are the new things that are happening other than just electrons, photons, and EM-wave that we've been playing with? There's a whole new area coming up with biology in which we're dealing mostly with neurons, and this is another new form of particles that through the proper integration with math, we think there will be a lot of interesting applications. So the next slide illustrates one of those applications. Here is You can see this is a MEMS space, a sensor electrolyte array that's fabricated using silicon MEMS technologies. And these arrays then has all the electronic sensing electronic on top of it. It's implanted into the brain. In this case, the experiment was conducted with monkey. They were implanted into the monkey brains. And the goal here is to watch the brain, these signals, and not just watch these signals, but process it, and most importantly, predict what the monkey will do. So this is much more advanced than just sensing, but it's also there's involved estimation predictions. And with that, we will be able to predict if a monkey wants his hand, move his hand towards right or to his left. And with all those information, we will now be able to help out patients who might have motions problems. Other areas that we're also making fronts is in the imaging area, medical imaging areas. NMR is, of course, one of the two that's becoming more and more popular, and with improvement in the algorithm that process the image. This is, again, advancement in math. We're now being able to see much more details in the heart regions and also view the vessels in the leg. So these are tremendous improvement in the imaging is purely just by advancement in the math. Of course, advancement in physics will also help in medical imaging. The next slide illustrates one such improvement. At this point, NMR, though is very powerful, it's usually not performed on children for a couple of reasons. One is it's very hard to convince the children to stay motionless throughout the entire process. And if they move around, the image will get blurred. And so a lot of time, the student has to go through enthusiastic if they want to go through this kind of process, which is kind of expensive and lengthy. So by improving the system capability, both in increasing the magnetic field and also the sensing circuitry, we're now able to conduct this image as significantly for the time in terms of minutes rather than half an hour or so. And these imaging will allow us to perform NMR on children, which in many cases are beneficial. Okay, what are other areas that we think there will be new horizons? These are in the energy and environment areas. Of course, these are areas that everybody's now have a lot of renewing interest. And a couple areas that we're focusing on, one is the energy areas. Stanford is, of course, well known for our research, breakthrough research in solar cells. In fact, one of our former colleagues is the founders of Sun Power. Now that with silicon solar cells already in large-scale productions, we're looking at different alternative material. So the next slide illustrates to you one of those materials we're looking at, which is organic solar cell materials. This is done by Professor Peter Pumans. And here we want to build the solar cell using material that can be sprayed on, very low cost, on flexible substrate, so that you can roll up these solar cells or stack multiple layers of these solar cells to increase its efficiency. So again, these are breakthrough technology that will, without any doubt, one day will find applications. In the environment area, our focus had mainly on imaging, looking from the outside world back down to Earth and look at these how the environment may impact our conditions, living conditions, and these are just some examples of those. Although these are not environmental focused yet, but the same technology will allow us to look at environment issues. So these are imaging of volcanoes, glacier velocity. Of course, this allows us to detect global warming much more effectively, and it's also maybe even one day allow us to predict earthquake in California. So these are, again, based on technology that are largely available already, but combining with more advancement in the math, which allow us to achieve all these imaging techniques. Okay, at this point, we have no doubt that the future is very exciting. With the addition of nano and bio neurons in these physics areas, we're now exploring new quantum effects. We're looking at new devices, new technologies. In the environment, energy and environmental initiatives, we are expanding our applications of our existing technologies. Now, without any doubt, we're dealing with increasing complexity, so we need more development in the math area. So Professor Stephen Boyd will say a few more words about the developments in the math areas. if you look at all these exciting features, one result of course is just a lot of things that one needs to learn in order to capture these opportunities. So this is why we're here today, to tell you what we're doing to help you to learn these new material with reasonable amount of pain, not substantial amount of pain. Okay. Okay, we understand that we do offer a lot of courses through SPCD, but a lot of these courses tend to be very intensive because they're designed for our own students in which we expect them to practice in such areas. And a lot of the time we don't really want to go into depth. A lot of us just want to understand the physics, what are the basics, so that in one day if we need to use that, we can go into the depth further. Starting this summer, we're going to start offering these abbreviated version of these courses. They will be about 2 units, and they will cover all the essential materials, and they will have reduced workload. Now, in this summer, these 4 courses that are offered don't have projects, but they will, instead of having 10 weeks of instruction, they will have 8 weeks of instruction, so it will cover 80% of the material, and it will give you a good base to understand the material, and if you want to broaden your knowledge in these areas without a lot of pain, this is probably a good way to do it. These courses cannot be counted towards the master depth or breadth, so in case you're working on a degree, this is perhaps the only limitation, but it can be counted as other EE units. If you're working on a certificate program, they will be counted towards your certificate programs. If we see sufficient interest over the summer, then over the next year we'll start offering even more abbreviated version of just the regular SPCD courses. For example, a lot of the courses involve a project design. We understand that you're already working in industry, you have a lot of experience with project design. There's perhaps no need to ask you to conduct another project. So those courses will again be, the workload will be lightened, for example, by not asking you to perform the final projects. With that, I'd like to stop at this point and see if there are any questions from the audience.
Professor Wong, thank you very much for that introduction to both the opportunities in electrical engineering and also some of the courses that are offered. I actually have one question for you. If I were a student or a professional in electrical engineering and I'm looking to retool, does the EE department have useful resources on the website, or what should I do?
Okay, we have on our website a list of all the courses we offer, and you can click on that. And also some of the courses that also offer on SPCD, you can go for SPCD website to identify those courses.
Great, thank you.
Also, if you find a course that are offered on campus but not on SPCD, you can always request to come to campus and attend those courses too.
Terrific. That's great advice. With regard to these 4 courses, they are each 2 units, which, as you mentioned, reduces the load. What kind of indication would you need from industry students who may be interested in terms of maybe doing this for a broader series of courses? What are you looking for? We're now experimenting with this approach, so we're looking for suggestions from the industry. If you look at a course and you like to see some of the contents, taken out or removed for the abbreviated course, we're certainly open to those suggestions. Now, if you want to find out more about these courses, what's going to be covered this summer, you can actually click on our website. There's a link for summer courses to be offered this summer, and you can click on it. The syllabus for all these courses are posted, so you can actually tell how much of it is going to be taught. We also describe what material we have taken out, so you can also tell what kind of material you'll be missing. Those are great resources. Professor Wong, I want to thank you very much. And if you have questions as we go through the program, we'll take those at the end. And with that, I want to turn it to Professor Stephen Boyd, who will actually drill down on 2 of the 4 courses that we have talked about here today, or have highlighted. The first one is EE 263. Professor Boyd?
Great. Thanks, Paul. Also, thank you, Simon, for giving a very good overview and setting the stage for the things I'm going to talk about. I'm going to actually talk about, in much more detail, 2 specific courses. That's EE 263 and EE 364A. slides I have here are culled from the course material. I won't cover all of them, but I'll just give you just a quick flavor of what these courses are about and how it fits into the big picture and why you might want to know about this material. Also, I'll say something about how it fits in with the general trends that Simon was describing. I should mention that both of these courses, all of the material for the entire course, all material is available on the website. Just go to Google and type in any of these things, and you'll find them immediately. That'll give you a really good idea to find out if you want to know what's in these courses. And you'll find out that, in fact, there's a lot in these courses, and that's sort of the idea behind the S versions, the abbreviated summer versions, is to make these go down to something which is to an essentials idea. So let me talk about 263 first. This is the course Linear Dynamical Systems, and the basic topics covered is linear algebra and applications. I should say in the broad scheme of things, this is one of the very core courses that Simon referred to as one of the mathematical ends. And I should say how that fits in. We consider ourselves consumers of or beneficiaries of Moore's law. So while people like Simon and his colleagues work out the technology to keep this relentless scaling going on, we're the ones who figure out cool things to do with all this power. So for us, it's a lot of fun because otherwise a lot of this stuff would be just math. But what's cool about it is it is math. The really cool part is it's also in your iPod. So I mean, and your cell phone. So anyway, all right. So let me talk a little bit about that. 263 the main topic is basically applied linear algebra. And part of that we talk about linear dynamical systems, and we do a little bit of quadratic control and estimation. Now, one question is, why would you want to study linear systems? Well, my opinion is that these are interesting because they come up in tons of applications areas, and by the way, well beyond EE these days. So the most obvious ones are automatic control systems. For vehicles, but for many, many things. Many products have embedded control systems in them. Signal processing has now moved towards something where basically all modern signal processing uses linear dynamical systems, almost all. It's making a huge impact in communication, so that if you want to do modern, wireless communications, you have to know this material, kind of, period. But it's also got a lot of other applications. It's in areas like economics and finance, which is kind of cool to learn one area of applied math that has applications in lots of areas. Simon already mentioned this, that in fact it's the basis for things like SPICE and circuit simulation at the end of the device simulation. At the end of the day, a lot of these things come down to solving large sets of linear equations, maybe many times, but that's the idea. Also comes up in mechanical and civil engineering, aeronautics, navigation and guidance, and this is just a first, just a short list. I mean, other areas would be statistics and operations research and areas like that. So there's a lot of applications now that depend on this type of material. Now, the usefulness of this, of course, depends on the availability of computing power. Which is now very, very large at this moment and increasing exponentially. There are many people using that word incorrectly. But here it's absolutely correct. It's just Moore's law. So these are things, if there's any, so we can. I mean, this is one of the things you can do with these. Absolutely requires large computing power. Now, you can use this computing power for analysis and design. That's clearly been done. But actually, more and more it's used in implementation and embedded in real-time systems. So more and more you find actually the control laws that run in things are quite sophisticated, involve more than some very simple calculations. They can actually be running full linear dynamical systems. As to how this fits in historically, digital signal processing, it started up, it traces to, let's say, MIT in the 60s or something like that. Maybe a bit earlier. Depends where you want to do the cutoff. But at first, that was a very advanced topic, taken by PhD students, and it was very expensive technology. Only the military would use it for very high-end products and things like that. Now, DSP, as you know, and again, this is just directly related to Moore's law. It's a consequence. It's now it is everywhere. It is an undergraduate class. It's in all electronics and so on. So, and I think the same thing is going to happen in the linear dynamical systems. That's really sort of happening now. That it is transitioning from, in the 60s, an esoteric advanced topic that you would use to guide missiles, to now something that's basically in all the products all around the electronics around you. So that's sort of that's the way I see this material, the trend here, and why it's interesting. I'll say a little bit about the origin and history of linear dynamical systems. Well, first of all, the math can be traced. Some of it can be traced to the 19th century, and it can be thought of as something like this. It's classical circuits and systems. That's the material from the 20s. That's transfer functions and poles and zeros and things like that. Kind of meets linear algebra. That's what this course is, really. Now, the first giant engineering application was aerospace in the 60s, which was really enabled by these methods. So, I mean, you don't do space stuff without this, period. But somewhere in the 80s, this transitioned from a specialized topic to one that's widely used, and one that, you know, a lot of you have to know if you do a lot of areas, and not just in electrical engineering, but other areas. And this is something like digital signal processing and information theory, which also transitioned from a very mathematical, very abstract area to one that's widely used all around in all sorts of applications. So I'm going to very quickly look at an example, just to give you a rough idea. I won't go through any of the details, as I said. All of the everything here can be found. Just go to Google and type in any string, and you'll find this very, very quickly. So I just want to see the kind, you know, what can you do with linear, if you know about linear dynamical systems, and I'll give you a rough idea. So I'm not going to go through the equations here, obviously, but we have a mechanical system with 16 degrees of freedom. Actually 8 degrees of freedom here, and we have 2 inputs and 2 outputs. You think of it as a mechanical system, some kind of motion control system, something like that. And you have 2 inputs and you have 2 outputs. And what you want to do is find an input that will move the output over to some desired thing. That's this 1 minus 2 vector. One thing you can do is just figure out what's the constant you should apply. You should figure out just what's the constant you should apply, and then do it. Now, if you do that, here's what happens. If you apply these constant inputs, what will happen is, and this is kind of obvious from intuition, if you take a mechanical system and apply some forces to it, it's going to shake. It's going to have vibration modes. And here it takes, something like 1,500 time units for this to converge. I've written seconds down here, but if you don't like that, you can consider these picoseconds or nanoseconds, depending on the application. Doesn't really matter. And you think, well, wow, the thing has all sorts of vibration modes. How could you do any better than that? And the answer is, you can. So, it's totally different at time axis here. This is 50 time units as opposed to 1,500. This is the input you should apply at one of the forces, and this is the input as the second one. And what happens is this. Here's the output, goes like this, and then converges exactly in 50 time units. Now, what I want to say about this is no one could look at these input signals here and say the following. Oh, yeah, I was just about to try that. These are not obvious. You have to know what you're doing to come up with signals like this. Now, this is the kind of thing you can do, if you want to know what the kind of thing you can do after you take 263 that you couldn't do before. This is one of them. I should add, there's a lot of practical applications of this. Let me just mention one right now. Let's take an XY stage where you have an extremely expensive machine, let's say for lithography, and you're printing a bunch of things. Well, how does that work? You shift things over a little bit. You have to wait, obviously, for it to stop shaking before you can actually do your print, because, as Simon pointed out, we're now doing lithography at way down at the nanometer level and things like that. So, what does this do? This says if you just shift over, 2 centimeters and wait for the thing to stop shaking, you'll wait a long time. If you know what you do and you apply an input to the XY stage to move it optimally, something like this, the whole throughput on your machine is going to be a whole lot higher. So I thought I'd mention one application of this. Another obvious one is disk drive head positioning, where a disk drive head will get a request to seek track 230, and if you can do it in 4.5 milliseconds, that's without, and arrive there without vibration, that's great. If it takes you 17, that is not great. So these are the types of things. Okay, I think I'm going to go over to 364 now and say a little bit about this class. So this class is basically about optimization, and so I'm going to say a few things about optimization. Just what is it and all that sort of stuff. I won't say much. Again, all of this and much more is available on the web, so you can get a very good idea of what what the topic is. Okay, so in mathematical optimization, by the way, you have to say mathematical here because in a broad audience, it can mean many other things. For example, if you type optimization into Google, it usually means something like website optimization or something like that. So, okay. So the idea is that you form a mathematical model of the problem you have, and it could be anything. I'll talk about what it might be in a minute. You have some variables. That's the x's. These are the things that you want to choose. And you minimize some objective function. That's how you decide how good the design is. And you have some constraints. And the constraint says that you won't consider any designs that violate these constraints. So this means you have to come in within budget, within time. Something can mean many things. And an optimal solution is just the one that meets the constraints and has the lowest possible objective. So what would be some examples? Well, here are some ones that people that you might know about. One would be portfolio optimization, and here your variables are the amounts invested in different assets. So how much you can invest in different assets or asset classes, and you have to choose. Well, the constraint was, one is you have a budget. You have a total amount that you're going to invest, but you might have things like a maximum or minimum investment per asset. You could have a minimum return, and of course you could have things like margin limits and things like that. Now the objective here might be that given all the constraints and a minimum return, a required minimum return, to minimize the overall risk or return variance. So this would be a typical objective in finance. A second one, quite different, would be device sizing in electronic circuits. So here you have a circuit. You've chosen the circuit topology, and you want to choose the width and length of all the devices. And of course you have manufacturing limits. You can't make it smaller than your fab is going to allow. And it's got to be fast enough. So you've got timing requirements. It's going to have to, whatever you're making is going to have to clock at 1.5 gigahertz or whatever it is. And you have an area constraint. The area, you might be given an area constraint that'll affect, well, the economics of the whole thing. And the objective might be meet all the constraints and optimize the power consumption. Why? Because that's going to give you your best battery life. These are just rough ideas. And a final area would be data fitting. So let me say a little bit about that. That's a very different thing. In the first two applications, you are choosing, it's things where there's action involved, like a portfolio optimization is how should I invest. Device sizing is how shall I build the circuit. In data fitting, it's kind of the opposite. You're actually using it to, you're looking at data. And here, what you're doing is you're fitting a model. So the variables might be some model parameters. There might be a few, and there may be a very large number. And you have prior information and limits on that. And the objective would be some measure of the misfit or prediction error. So this is what, so optimization is very widely used in data fitting, even to the point where some people would claim that all of data fitting and much of statistics comes down to optimization. I mean, actually, people in statistics would say that's an overstatement, but anyway. All right. So let's talk about solving optimization problems. You can form an optimization problem, and people do all the time. In fact, that's actually very useful because it's a clear way to think about what do you want. You actually write down the specs of what are you doing. What are the things you have to choose? What are the constraints? What is it you're really trying? How would you judge if it's good or not? So it's a good exercise just to form a problem. But the real interest, of course, is in solving them. Now, here's the bad news. It turns out most problems you can't solve. So sorry about that. Now, you can solve them in some compromised way. You can either have an extremely long computation time and be guaranteed to find the right solution, or you can have a fast way that's not guaranteed to find the solution, this sort of thing. Now, and this is what this course is about, there are some very important exceptions, and these are mathematical optimization problems that you can solve extremely well. So, I mean, you can solve them efficiently and reliably. And some you probably have heard of. One is least squares. They're ordinary least squares, and that's got lots of other names. In statistics, they would call this regression. And it's got fancy extensions like linear control, signal processing, filtering. A lot of things are really basically fancy forms of least squares. A lot of equalization in communications. They're just least squares problems. And these problems, you can solve them exactly. There's no compromise. You get it exactly, always works, you get the right thing. Now, another area that people in EE know less about, but historically it has been used in EE, is linear programming. That's another area where there is no compromise. And the parent, in fact, sort of the parent of all of these problems is convex optimization. So, I'll say a little bit. I think I'll jump through some of these things about the details of least squares. But least squares is very standard. You solve a very specific problem. You just minimize the sum of squares. That's all. And that's widely used for many applications and so on. Now, linear programming, that's a different thing. And this is something a lot of people in EE haven't seen, although I think it's going to make much more. It's going to be making an impact, and it is in several areas. In fact, as Simon already mentioned, one application was compressed sensing that we just saw. I mean, that's not quite linear programming, but it's very, very close. So a linear program, you minimize a linear function subject to some linear inequality constraints. Now, of course, the details here don't matter at all. But this is an interesting set of problems because for these problems there are no analytical solutions. So you're not going to hear about this in your math class. Generally, that's changing, and I hope it changes much more. But you're not going to hear about this because there's no analytical solution. It's just we can simply solve them. It's that simple. Convex optimization is sort of the parent of these, and these are mathematical optimization problems with special forms, and they include least squares and linear programs as special cases. And I'm not going to go into the details of what this means. That's not right here. What I really want to do is just give you a rough idea of what the course is about, what do you do with it, and so on. So for these problems, there's no analytical solution. But what's been developed in the last 15, maybe 10 years, depends on how you set your threshold on quality and efficiency, are very good methods to solve these things. So these are now, there's still challenges in solving convex optimization problems, but in many cases, this is just a technology. And so my opinion on this is that this is just this should be in your toolbox. In fact, it's a big tool. In fact, I'd even put it at the top of the toolbox, not in the bottom part. Because it can be used for lots and lots of things. Okay, now let me say about what the challenge is, but I turn it around and I think it's a positive thing. It's actually not that easy to say if a problem is convex. You don't know. There's a lot of tricks and so on. And it's not easy. It's not like recognizing a least squares problem or something like that. So you really have to be trained to do this. And people are finding these all the time. If you want to take the full 10-week course, you can get a rough idea of that. My own opinion is that's probably more than you need to know if you just want to use these things. And the hope is that the abbreviated courses will be something closer to what would you need to know to use these things. You're not going to know every detail and so on, but what would you need to know to use these things? Okay. Now the primary goal of this course is to basically is MUN modeling. It's on formulating problems this way. We do a lot of applications in the course, and I should warn you if you go to Google and type in this phrase, you will go to you'll see other courses at lots of other universities. Some are based on this course. Others are much more theoretical. So don't be put off by those. That's the traditional one, and that's something like that DSP course from MIT in 1965, which was super theoretical. So this is just part of the shift towards a more applications-based course. And I'll finish up by just saying a brief history about this. So the mathematics of it is 100 years old, basically, and was pretty well developed by 1970. There's a big Stanford connection because, in fact, one of the most widely used context optimization problem is linear programming, and the principal algorithm for that was developed by George Danzig, who was at Stanford for many decades, actually, I can say. Now, there was a lot of interest in the 60s and in the 70s. There were actually 2 times where advances in these areas landed on the front page of the New York Times. But I think, in my opinion, what is most interesting and most, I think, and the reason why I think people should know about this is there's just tons of new applications. And these are in areas like control, signal processing, communication, circuit design, machine learning, areas like this. So I think that's it's a very exciting time, and this is part of it's a tool that's being used in a lot of application areas, and these courses would be a very good way to get a rough idea, to get not a rough idea, a basic working knowledge in this area. So I think I'll quit there, and maybe there'll be some questions or something. I'd be more than happy to answer them.
Professor Boyd, thank you very much. We'll take questions as we close. What I'd like to do now is just turn and shift gears a little bit. We want to thank again Professor Boyd and Professor Wong for participating in this program, which gave you a reasonably good idea of where electrical engineering sees the future. Hopefully some of you see that as well. As well, we hope to try to give you a sense of some of the courses that will be the building blocks to create that future. You've heard about 2 of those courses. What I'd like to do now is shift gears and talk a little bit about how you can engage in some of the courses that you heard about today, and give you some background on the Stanford Center for Professional Development. Our center serves as the bridge between industry and Stanford University, and we offer graduate and professional education courses and programs to meet the career-long education needs of technology professionals, engineers, scientists, managers, and executives. SPPD has been part of the Silicon Valley actually for over 40 years now, and we believe, based on customer feedback and discussions with companies, the Stanford education provides new and innovative ways for companies and the people in those companies to create innovation, which leads to a more competitive Silicon Valley. SCPD's portfolio is outlined here on this slide. We offer graduate programs, the first of which identified here is the non-degree option, where students can take individual courses on a quarter-by-quarter basis for Stanford University credit. Many of the students who participate in this category actually can accumulate up to 18 units, get a very good sense of how courses and offerings are in a specific department. Often they can, in the domain, specific domain can be applied to a master's degree. So for instance, if you take a number of EE courses this summer and on a non-degree option basis, all you need to do is provide us with a transcript which proves that you can do the Stanford level work, and you will be admitted to that course, and you can continue to accumulate those credits toward a master's degree. We also offer graduate certificate programs. A number of the courses in this sequence that you have seen here today can accumulate toward a graduate certificate. Those are typically a specific area of study, usually 3 to 5 graduate courses. In electrical engineering, for example, there are 4 courses, and that's one very solid way to participate if you already have a terminal master's degree in this specific domain. Finally, we have a master's degree called the Honors Cooperative Program. This has been in existence since 1969. We have a number of degree areas. Electrical engineering is one of those. And you must apply to the department and get accepted as part of the cohort. You then have the full rights and privileges, and you have the opportunity to continue to work as a professional while taking this degree on a part-time basis. Finally, we have an audit program. These are courses where students can observe the class, not participate with homeworks and assignments in an interactive way, and no credit is earned, but this may give you a sense of a particular course or domain. SCPD conducts 95% of its business at a distance. We offer live lectures online, and those lectures are available during the active quarter 24/7, and we allow you to keep pace with the lectures at your convenience and in around your work and family schedule. The courses typically have homework assignments with them. We ask that you submit those homeworks through the SCPD so we can help monitor them, as well as follow along with the faculty requirements. They may have you make a double submission, but this is a great way to make sure that you're secure. We do have a requirement in the event that the course has a test. We ask that you identify an exam monitor, not your best friend or your wife, but instead your boss or someone in HR. This will allow you to observe the rules and requirements that Stanford University has for conducting that test. Here are the ways, I'm going to walk you through a little bit of how you can enroll. The summer quarter is open now for enrollment and will remain open until June 17. If you're interested in enrolling in electrical engineering courses this summer, or any other graduate courses, we offer 40 this summer. You must enroll online through SCPD's website at scpd.stanford.edu. We do require an official sealed academic transcript. However, we do accept copies as that official transcript is being routed to us. Tuition is identified in a number of categories. The higher rates are for the non-degree option student, as if you don't participate through a member company. Our website identifies member company. On a per unit basis, there's a significant cost savings, and typically courses are 2 to 4 units. As you saw, we have a new pilot program, an experiment this summer with the 2-unit courses in electrical engineering. The audit tuition on a per course basis for non-member companies is $11.50, and if you're a member company, the audit tuition is $995. The enrollment deadlines and assistance located on SCPD's website. I'm going to walk you through a little bit of SCPD's new website. We have something called My Stanford Connection. Many of you who participated in this webinar actually enrolled through this. We thank you very much. This is the way that you can access courses and information about SCPD. We'll have the latest announcements. As well, you'll engage and you'll see your course videos through this link. Here's an example. If you were to do a search on a specific course, you would identify that domain or the specific course if you know the name, and then you would go to this page in the course section, and you would hit the button Enroll in this section, which is highlighted. That would lead you to completion, and you would hit this cart, which is in the upper right hand of the screen when you're in My Stanford Connection. That you click on that cart as much as you would do in Amazon.com or similar application, and that will position you to a registration page to make sure that your basket is correct, and then you would be asked to provide payment at that time. Well, what I'd like to do now is take a quick poll. Again, I mentioned a couple of different ways to engage. We are still welcoming questions into the queue. But here what I'd like to know in this poll is, are you interested in enrolling in summer courses in electrical engineering? There are a couple of choices. I'm ready to enroll this quarter. Summer quarter is not right for me, but I'm interested in EE courses later in the year in September when the traditional academic year starts. I'm not interested, but I know colleagues who may be interested. Or finally, I'm not interested at this time. So if you could make your selection, I would appreciate it. A few votes are still coming in. Alrighty, I'm going to close the polls now. And it seems that some people are actually ready to enroll. A few of you are interested, but summer's not the right time. Somebody knows a colleague who may be interested. We'd love to follow up with you. And some of you may have are just viewing this and not ready at this time. So we hope that maybe you'll come back to us at a later time when you are ready. As I mentioned, SCPD not only offers graduate courses and professional education on a year-round basis. Most of the offerings are online, but we also offer free webinars. Our goal in offering these webinars is to create a learning community. We have some free stuff, or webinars, seminars. As well, we have graduate and professional education courses, which we believe will help you on your journey. The next webinar we will offer is on June 24. This will be from 9 to 10 a.m., where we will be joined by Maggie Johnson, who's the Director of Educational Affairs and Undergraduate Studies for the Computer Science Department, and also has a role as a Learning and Development Manager at Google. She has done a lot of work in IT management, and she'll be talking about contemporary IT benchmarking and analytic forensics. Perhaps she's using some of the tools that Professor Boyd talked about. We look forward to having you join us on that webinar. And with that, we are nearing the conclusion of our webinar here today. I'm going to encourage you to follow up with SCPD. Keep in touch. We have a number of courses, some of which you heard about here today, and I've listed them on this slide. If you're interested in following up with those on registering for these courses, you can simply click on the link here, enroll.stanford.edu. You can also encourage your company to become a member so that you and your colleagues continue on the journey for lifelong education, something that Stanford views as vitally important to the vibrance and competitiveness of the Silicon Valley and beyond. With this, we'd like to thank you here today. We still have some questions in the queue. We'll be continuing to answer those offline. We wish you the very best, and this concludes our webinar. We thank you and have a very good day.